Topic 11 to 5G Introduction. Topic 11. Overview. Describe evolution of mobile standards from 1G to 5G. Describe use case of 5G. List the 5G specifications. Describe 5G spectrum and its challenges. List differences between 5G versus 4G. Describe 5G network architecture in terms of standalone and non-standalone systems. Core network, radio network access, massive MIMO and beamforming, supplementary uplink technology, network function virtualization, network slicing, 1G to 5G, the evolution of mobile standards. Wireless communication technology inside cell phones and other mobile devices has evolved over several decades, starting with the then revolutionary 1G, referred to as the earliest form of voice-only network, all the way to 5G. First off, the G in 4G or 5G stands for generation, and the number is just a representation of the evolution of technology. 5G design use case. The fundamental idea behind 5G is a single network that is flexible enough to handle a variety of different use cases. In 2015, the International Telecommunication Union (ITU) defined a vision for 5G in three major areas, also known as the 5G triangle. 5G key uses. NHANCED mobile broadband, EMBB, providing significantly faster data speeds and greater capacity of 10 gigabits per second. New applications will include fixed wireless internet access for homes, outdoor broadcast applications, promising greater connectivity. Ultra-reliable low-latency communication, URLLC, boasting 1 millisecond latency. This will be one of the biggest game changers once 5G is fully deployed. Mission-critical, including real-time control of devices, industrial robotics, vehicle-to-vehicle communications and safety systems, autonomous driving, and safer transport networks. MMTC, massive machine-type communication, 1 million connections per square kilometer, will aid in the development of the IoT, e.g. sensors in a city providing real-time coverage and update. 5G specifications. 3GPP members meet regularly to collaborate and create cellular communications roadmap for 5G technology. 3GPP defined standards for 5G, and standards are released into Release 15, 16, and 17. Specifications as follows. Up to 10 gigabits per second data rate, greater than 10 to 100x speed improvement over 4G and 4.5G networks. 1 millisecond latency, 1000x bandwidth per unit area. Up to 100x number of connected devices per unit area, compared with 4G LTE 99.999% availability. 100% coverage, 90% reduction in network energy usage. Up to 10-year battery life for low-power IoT device. 5G spectrum. 5G needs to be available at all spectrums. Therefore, two key ranges have been determined. Frequency range 1, FR1, the sub-6 GHz band, which is the low-frequency band and the primary band of 5G. The frequencies below 3 GHz is called sub-3 GHz, and the other frequency bands, 3 GHz to 7 GHz, are called C-bands. Frequency range 2, FR2. The high-frequency bands from 24 GHz onward are known as mmWave. 5G spectrum challenges. The challenge for mmWave is signal attenuation, whereby buildings and objects in the line of sight can be disrupted. The challenge can be mitigated by solutions, as illustrated. The key differences between 4G versus 5G network architecture include the following. Latency. 5G's 1 millisecond versus 4G's greater than 60 milliseconds. Potential download speeds. 5G's 10 gigabits per second versus 4G's 1 gigabit per second. Base stations. Cell density. OFDM encoding. 5G base station. 4G transmits signals from macro cell towers. However, 5G uses small cell technology due to its faster speeds and millimeter wave frequency levels, so carriers will deploy high-band 5G in small cells about the size of pizza boxes in multiple locations. Small cell technology enables 5G to provide more cell density and enhance network capacity. 5G OFDM encoding. OFDM is used to split different wireless signals into separate channels to avoid interference, which also provides greater bandwidth. Because OFDM encodes data on different frequencies, this can bolster 4G and 5G download speeds, as these networks would have their own signal channels rather than a shared one between them. 4G uses 20 MHz channels, while 5G will use 100 MHz to 400 MHz channels. 5G network architecture. This section will describe the key technologies and architectural changes in 5G. Standalone SA and non-standalone NSA systems. 5G core network, radio network access, massive MIMO and beamforming. Supplementary uplink, SUL network function virtualization, network slicing. Non-standalone versus standalone SA 5G, but will appear in applications where connectivity is shared with existing 4G LTE in what is called non-standalone NSA mode. NSA mode, 4G core network known as Evolved Packet Core, EPC, is reused to quickly introduce the 5GNR technology without large financial outlay. SA mode, 5G core network and radio access network, needs to be built with significant financial outlay. Supports EMBB, URLLC and MMTC and network slicing. Non-standalone versus standalone SA. As more and more 5G network infrastructure goes online over the next several years, it will evolve to enable 5G-only standalone mode, SA. This will bring the low latency and ability to connect with massive numbers of IoT devices that are among the primary advantages of 5G. This method allows integration of 5G with 4G and allows 4G to phase out in the future. 5G core network. For 5G, the core network is being redesigned to better integrate with the internet and cloud-based services, and also includes distributed servers across the network, improving response times, reducing latency. That is why this architecture is also called 5G Core Service-Based Architecture, SBA. 5G Radio Access Network, RAN. RAN consists of various types of facilities, including small cells, towers, masts. 4G Core, on the other hand, is often centralized and further away from the base stations. This architecture makes high-speed, low-latency, end-to-end communication challenging. 5G Core is now flexible, decentralized 5G nodes. For example, 5G Core functions can now be co-located with applications in an edge data center. This makes communication overall paths short, reducing the strain on the backhaul network. 5G Massive MIMO technology. 5G will use massive MIMO, multiple input, multiple output, antennas that have very large numbers of antenna elements or connections to send and receive more data simultaneously. Beamforming is a complementary technology that allows the massive MIMO base station antennas to direct the radio signal horizontally and vertically to the users and devices rather than in all directions. 5GNR uses broadcast beamforming technology to determine the best path for the radio signal to reach the user. This increases efficiency as it reduces interference, unwanted radio signals. 5G Supplementary Uplink, SUL technology. Supplementary Uplink, SUL, is introduced in 3GPP Rel 15 to extend the uplink coverage by providing a supplementary uplink, usually in sub-3 GHz band. SUL is adopted to compensate the C-band's short uplink coverage. In areas of restricted uplink coverage problem can be effectively compensated by switching the uplink to the 1.8 GHz band, while downlink is maintained at the 3.5 GHz band. 5G network virtualization and slicing. Network functions virtualization, NFV, is a network architecture concept that uses the technologies of IT virtualization to virtualize entire classes of network node functions into building blocks that may connect or chain together to create communication services. Network slicing. 4G services go through a single pipeline, and it is not able to meet diversified business scenarios. 5G uses network slicing, and it is a type of virtual networking architecture that allows multiple virtualized and independent networks to support particular customers and business needs. Summary points. 5G developed around the three business use cases, namely EMBB, URLLC, and MMTC. 5G started with NSA approach to save cost and for it to integrate with current 4G operations better. 5G utilizes methods like macro cells to better manage its coverage. 5G takes on a decentralized approach to reduce bottlenecks. 5G relies on the software to virtualize its operations so that network slicing can take place.